And shifting to my presentation, I would like to remind you what is a beat phenomenon here. So there is here a sound generator emitting, two sounds at different frequencies. And you remember, if the two frequencies get very close to each other, but not being identical, you will hear a modulation, in amplitude, of the sound, So just a reminder. So I tried to make it work. Do you hear? Change. So there is a frequency of the sound, which is quite loud, quite low frequency. But then you may hear the modulation. Did you hear it? No? So this is the maximum sound. So something like that. Okay, now I come to the core of my presentations. Table of contents, You remember yesterday? Well, there was a brief introduction, general introduction, then I proceeded with some reminders, and namely the complex representation of an electromagnetic wave. What we established yesterday is that the expression of the electric field, could be shown as follows. Real amplitude, times complex exponentiation where you see the space coordinates, and then an additional one where you see the dependence as a function of the time. So it is an expression to which I shall refer today, so I just indicated it here. Then we spoke about the principle of Huygens Fresnel, you remember, combining the constructions of Huygens, for the propagation of electromagnetic waves, with the idea of interference between the secondary wavelets. Oh, then it was a brief history about the measurements of stellar diameters, and you remember, we saw that our ancestors thought that the diameter of the stars was about 2 arc-minutes, and this is a angular resolution of our own vision, our own eyes. So a pupil, which size is about, varying between 1 millimeter and 5 millimeters. Then Galileo, while sitting inside behind a rigid wire, measured the angular diameter of Vega as being about 5 seconds of arc, and then we saw that this diameter, was in fact the result, of the seeing effects, atmospheric seeing effects. Then Newton, very bright, you remember? Well, it reminds me the song of the Beatles, The Fool on the Hill, And the song says that the fool on the hill sees the sun going down, and the eyes in his mind sees the world spinning round, And I think Newton could have been, a very good Beatles, And because he got a very good estimate, of what the angular size of a star should be, So he just thought about the sun, and he said, place it at the distance of Vega so that it would appear as a 0 magnitude star. So using the relation between magnitude and luminosity and distances, he inferred that the angular diameter of the sun would be of the order of several milli-arc-seconds. Well, then came Fizeau and Stefan, who proposed to derive the stellar diameters of stars while observing, most of the bright stars with the 80 centimeter Marseille telescope, which was 80 centimeter, and they could not see the disappearance of the fringes, while using the mirror as a basic interferometer. Okay, then we ended up, with the construction of our small milli-interferometers, and you understood, yesterday how it worked, And okay, so today we will continue, and with a very important chapter about light coherence, And the first subsection is about quasi-monochromatic light. Okay, so light coherence is a theory, which essentially consists, in a statistical description of the properties of the radiation field in terms of the correlation between electromagnetic vibrations at different points in the field. So, I will explain you what does that mean, yeah? Okay, so as you know, we are not observing, usually with an extremely narrow band filter, but with a narrow band filter which has a certain width, yeah? And sometimes it's a broad band filter, yeah? So here I have represented the spectrum of a white dwarf, and I've just isolated, yeah, the narrow band spectral range that we use, yeah, for our observations, yeah? So it is centered around the frequency nu, and the width, yeah, is 2 delta nu, so it's the frequency passing through the filter or nu prime belonging to the range nu plus or minus delta nu. Yep. Now, well, just as for monochromatic light, yeah, we can define the intensity of such a radiation field. So we saw that the intensity was the time average, yeah, of the electric field, Vt, multiplied by its complex conjugate. Well, in this case, yeah, the electromagnetic field, yeah, consists in the contribution, yeah, of many electromagnetic waves emitted at frequency nu prime in this range. Yeah? So what shall we do? Well, we may just write that the electric field, yeah, is integration between nu minus delta nu and nu plus delta nu of, well, the real amplitude. So I would say a nu prime, because, well, it could slightly depend on the frequencies, multiplied by all of these. Yeah? So I could write E2 pi nu multiplied by, well, here I put nu prime, of course, times T. Now, minus what? It's Z over lambda, but lambda is C over nu. So here I can just divide this one by C. And now integrating in this spectral range. Do you agree with that? Or is there any difficulty? So this represents the contributions of all the electromagnetic radiation, yeah, contributing at frequency nu prime in this spectral range. Now, what I will show, yeah, is that in fact the resulting electromagnetic field will still be a field oscillating with a frequency nu, yeah, but with an amplitude subject to the beat phenomenon. Okay? So how do I proceed? Well, there is a little trick. I will just insert here inside the integrand, yeah, the following quantity. E minus 2 pi nu time minus V over C. And now I put it here, it's conjugate complex, I put nu times T minus C over C. I can say that the representation of the electric field takes the following form. It is an amplitude which will depend on the space and time variables multiplied by this quantity. Nu times T minus Z over C. Now, well, I have to represent what is this quantity. Yeah? Of course, this quantity should be equal to all of this. Yeah? So it will be integration from nu minus delta nu, nu plus delta nu of nu prime multiplied by E 2 pi nu multiplied by first I will do like this, nu minus nu prime, now multiply by T minus Z over C. d nu prime. Do you agree with that result? Yeah. So this is essentially this quantity. Yeah. Now to show you that this amplitude, which is a complex amplitude, yeah, varies, yeah, with the frequency of the bit phenomenon, yeah, I will do the following. I shall assume that the amplitude A of nu prime is a constant. It means that, well, over this spectral range, yeah, the amplitude doesn't vary significantly. Yeah? So let's assume that A nu prime is a constant. So it's equal to A0. So this quantity will become equal to A0 multiplied by, and now I will make a change of variable, yeah? Excuse me?
The power of 2 pi I nu is the sign already because you have plus nu prime in this equation, but you have a minus.
Yeah. So you will do like that. It's okay? Thanks. Yeah. So I will make a change of variable. Let's define W, yeah, as being equal to I 2 pi nu prime minus nu times T minus Z over C. Now dW will be equal to I 2 pi times T minus Z over C multiplied by d nu prime, okay? And that's all, yeah. So this will be equal to, so I should change my limits of integration. If I put here nu minus delta nu, it will be here minus I 2 pi delta nu times T minus Z over C, and here to plus I 2 pi delta nu times T minus Z over C multiplied by E, this is W, times d nu prime, which will be dW divided by I 2 pi times T minus Z over C. Correct? So now it's easy to perform this integration. It will be A0 divided by that quantity, I 2 pi, times T minus Z over C, multiplied by this quantity, yeah, that I evaluate for the two limits of integration, yeah. So it will be E I 2 pi times delta nu times T minus Z over C minus E 2 pi delta nu times T minus Z over C, and I close my parentheses. And now here, you see, it's just E ix minus E minus ix, yeah? So this will be 2 times I times the sign, yeah, of the argument, yeah? So it becomes equal to A0 divided by, so the I and the 2 will disappear, so it will be divided by pi times T minus Z over C multiplied by the sign of 2 pi delta nu times T minus Z over C. Okay? So what I see is that the complex amplitude, yeah, varies as a function of time, but not anymore with a frequency nu, which is extremely fast, yeah, but with a frequency delta nu, which means that it's a very slow variation, yeah. And so this is a result, yeah, of combining, yeah, light radiation, yeah, within a narrow spectral range, is to get quasi-monochromatic light, yeah, but it does still oscillate with the frequency nu, but the amplitude, yeah, varies very slowly with the frequency delta nu. Okay, and this is shown maybe, okay, this is a demonstration. here. So while combining beams of electromagnetic radiation at a frequency nu prime in a narrow band range, it's equivalent to get finally a quasi-monochromatic light, which still varies with the frequency nu, but which amplitude is subject to the beat phenomenon. Okay. So what I've said now is in terms of a time dependence. Now you could wonder, what if I freeze the time and I look at the train of radiation as a function of the distance? Well, it's easy. We know that, so the period of the beat phenomenon that I could tell t is equal 1 over delta nu. Okay, now, if you prefer to look at the phenomenon as a function of time, so we see that the spacing between two maxima here is 1 over nu. So it's a very short period. And now, if I look here, what is the time interval between the two blue lines? Well, it's the period of the beat phenomenon, 1 over delta nu. Now, I may look in a different way along. I'm not considering anymore the time variation. I freeze the time, and I look as a function of the distance. How does this train of electromagnetic radiation varies? So what I do is the following. I say, okay, nu is equal to C over lambda. Do you agree? Nu equals C over lambda, which means that delta nu is equal to minus C over lambda square times delta lambda. Yes? Okay, now, what do? I will do the following. I will say, okay, in terms of wavelengths, L is equal to C over delta nu. So I divide C by delta nu. And now I see that C over delta nu is equal, well, in spite of the negative sign, to lambda square over delta lambda. Okay? So I see that this length is much longer than the wavelength. And this is called the coherence length of the field of radiation. So this is a function of distance. So this is the coherence length. So this is the first very nice result. Because if you would like later to take two beams of radiation and let them interfere together, well, one condition is the following, is that the difference in the trajectories of the two light beams coming in the focal plane should be less or equal to the coherence length of the light. Now, if you take as Michelson a wavelength of 5,000 angstrom, a bandwidth of about 1,000 angstrom, you find that this is of the order of 1.5 microns. And this was the accuracy with which they had to establish where the difference in length of the two beams coming into their interferometers. So using a beam of 7 meters on top of a telescope, etc., they had to make sure that the difference in length was less or equal to a few microns. And this is the difficulty of optical infrared interferometry. At radio wavelengths, you are much more relaxed. The constraint is just that, well, if you are good within a few centimeters, it's good. And for engineers, this is not a hassle. Okay, so this is already one thing. Now, we could wonder now, what becomes the visibility of the interference fringes in the Young's Hall experiment for the case of quasi-monochromatic source having a finite dimension? So yesterday, when we considered the Young's experiment, we considered that the two holes were infinitely small, that the light source was infinitely small, and that the light was purely monochromatic. So now we will try to relax all those hypotheses. So first consider that it's quasi-monochromatic light, not monochromatic. then the source is not point-like, yeah, is a finite dimension, and then later on that the holes in the screen of Young are not point-like but have a finite dimension, just like apertures of telescope. Yeah. Okay, so to do that, yeah, well, I still consider the Young screen here, well, still with 2 point-like holes, still P1, P2, and a source of light with a finite dimension, and emitting quasi-monochromatic light. And what I'm wondering is, well, given a point Q in the screen of the observer, what is the resulting intensity? What we did before is that I can represent the electric field as complex amplitude, varying, yeah, very slowly with a frequency delta nu, multiplied by, well, this frequency still is a function of time, yeah? Okay. So, well, I know that, okay, the intensity, yeah, at the point Q will still be equal to the time average, yeah, of, well, the conjugate complex of the electric field multiplied by the electric field itself, yeah? Now I may wonder, but what VQ at the time t is equal at, yeah? Do you agree? Well, it will be the contribution, yeah, from the first hole number 1, but evaluated at the time t minus T1Q, where T1Q, yeah, is the propagation time for the light to go from the first hole to the point Q, plus, say, well, the electric field, yeah, coming from the hole number 2, but corrected for the propagation time, T2Q, T2Q, like that, yeah? Now I will make just a translation in time. Let's assume that I define T prime equal T minus T1Q. So I will say, okay, VQ as a function of time T prime is equal to V1 at the time T prime plus V2. Okay, so T now is equal to T prime plus T1Q, so it's minus T2Q, T1Q, like that, yeah? Now, I define the delay between T2Q and T1Q as being tau, and I may rewrite this expression VQ as a function of T prime is being equal to V1 at time T prime plus V2 at times T prime minus tau. Yeah? And now I still make a time translation, yeah? I shift, yeah, the needles on my clock. I say, okay, I may write this as follows. So I don't need the prime, okay? So before it was Indian time, now it's Belgian time. Okay. Now, what next? Well, I will insert this expression into this one because I'm interested by the expression of the intensity. Yeah? So, what I will get is that IQ is equal to, first of all, I will have V1 conjugate complex times I will have V1 of t plus I will have V2 times t minus tau times V2 t minus tau. Then I will have plus V1 t times V2 t minus tau plus V1 t times V2 conjugate complex t minus tau. tell me if you agree with that. Yeah. So I have 2 factors here, 2 here. Then I just distribute, yeah, and I get 1, 2, 3, 4. Yeah. Now let's assume for simplicity, yeah, that my 2 holes are identical. So the 2 holes are identical, yeah. So what does this represent? Well, this represents, in fact, the intensity due to hole 1. This is also a time average, yeah. So this represents, yeah, the intensity of hole number 2. But since I consider that my 2 holes are identical, yeah, I may say that, okay, I may rewrite this expression as I plus I, where I, yeah, are the intensity due to hole 1 plus hole 2. And this is what I would expect if I had no interference of light. That at a given point Q, I'm receiving contribution of hole 1 and hole 2. But there is interference. And this is where it comes in, yeah? So plus, now I can do the following, plus V1 star times V2 t minus tau plus time average of V1 times V2 conjugate complex t minus tau, like that. Yeah. Okay, so we are doing some good progress. Now I should like to simplify, yeah, the summation of these 2 terms. Yeah, and does anyone know the answer yet or no? If not, yeah, I will make a small digression. Yeah. Well, let's consider 2 complex number Z1, which is equal to the real part plus the complex part, and Z2 equal A2 plus I times B2. Now, you know the answer, yeah? Yes. Theoretical physicists know the answer. Astronomers don't. But we know how to establish, yeah? Which I think is the most important, yeah? Not to remember anything, but to be able to recover the results, yeah? So now what I shall do, I shall make Z1, Z2 conjugate complex plus Z1 conjugate complex times Z2. So it just reminds you what we have here, yeah? Yeah. So let's try to find what it will be equal to. So it's A1 plus IB1 multiplied by A2 minus IB2 plus A1 minus IB1 times A2 plus IB2. So this is equal to A1 times A2. Now, minus minus, yeah? So it will be a plus B1, B2. Okay. Now I still have A1, A2. So this is twice. And now I will have minus, so plus B2, B1, B2, so it's correct. Plus I multiply by, so I will have A2, B1, A2, B1 minus A1, B2. And now here I will still have A1, B2, or A1, B2, correct? So A1, B2, so it will go away, right? And then the other one, minus A2, B1, so it goes away, yeah. So what I find is that this result is just that. Now, let's do something different. Let's try to take Z1 star times Z2. So this is easy. Z1 star times Z2, yeah, is A1 minus IB1 multiplied by A2 plus IB2. So it's equal to A1, A2 plus B1, B2 plus I, and I don't care about that. Because what I notice immediately is that this quantity is twice that quantity. And that quantity is just the real part of Z1 star times Z2. So I can say, okay, this is also equal to twice the real part of Z1 conjugate complex times Z2. Yeah? So here, I may write, I may continue and say, okay, this is equal to 2i plus 2 times the real part of V1 conjugate complex multiplied by V2 at the time t minus tau, like this. And now, what I do, look, I multiply here by I, and I divide here by I. Okay? And this quantity, well, this quantity here is what gives rise to the phenomenon of interference, yeah? And it is called the, do you know how it is called? So what? Well, it's a correlation coefficient, yeah, but it's a complex amplitude, yeah, of mutual coherence. So the correct naming, yeah, is a complex amplitude, yeah, of mutual coherence. Yeah. The intensity in the observer screen, yeah, is equal to 2i multiplied by 1 plus well, the real part of gamma 1, 2, which only depends on tau, where gamma 1, 2 of tau is equal to the time average of, well, the correlations between the two fields, the two points, like that. So this is called, this is named the complex amplitude of mutual coherence. So the intensity in the observer screen is equal to what? Well, the contribution from the two holes, plus their interfering contribution, which is twice intensity multiplied by the real part, of the complex degree of mutual coherence, So you see, this is a correlation, coefficient which measures the degree of correlation, of the two electric fields, at point 1 and point 2. Okay. Now, I should like still to simplify, the expression accounting for this factor, and I shall proceed as follows, Okay. Well, I know that the expression of Vi as a function of t is equal to, so I make use of this expression. Well, it's a complex amplitude multiplied by I2 I nu tau. So if I multiply V1 conjugate complex by V2 for t minus tau, I will find that it's equal to A1 Ct multiplied by A2 conjugate complex as a function of z t minus tau, exact, Now, multiply by this quantity, and then the conjugate complex of the other one. So what will remain, essentially, is the exponentiation of I2 pi nu tau. Because the multiplication of this factor by its conjugate complex will be equal to 1. So it will just disappear. Okay? So this is what will remain. Now I will have to take the time average, but this does not depend on time. Yeah? So the time average will be equal to this time average. Now let's divide it by I. And what I obtain, well, is just the expression of gamma 1, 2, function of tau. Okay? Now, if I would take the module of this expression, so the module of gamma 1, 2, or what I could still do is just to say, well, another way to account for that expression would be to write that the complex degree of mutual coherence is equal to its module, gamma 1, 2 of tau, multiplied by something to make this quantity complex. So I beta 1. Do you agree with that? That gamma 1, 2, gamma 1, 2 of tau, which is a complex quantity, is equal to its module, multiplied by something in that plane. Okay, but now the module of gamma 1, 2 of tau is equal to what? Well, is equal to the module of that, but the module of this is 1, so what will remain is the module of A1 z tau multiplied by A2 z t minus tau, like this, divided by I. You agree? Now I will make an assumption. I will assume that tau, so the time delay, is much smaller than the period of the bit phenomenon, which is 1 over delta nu. So it means that, well, I have a very good, I have a very small time difference between the two beams coming at the point Q. If I do that, I can say, well, I know that, the electromagnetic field of radiation, which varies with the frequency nu, is an amplitude which varies slowly. But if I assume that the time delay is very small, it means that taking it for tau or for tau equals 0 is about the same. Okay, it's a good approximation. So I may say, well, this is also the same value for tau equals 0. And this is equal to gamma 1, 2 for tau equals 0. Okay. So this is essentially due to the fact that the amplitude varies very slowly. And if I make the assumption that the time delay is much smaller than the bit phenomenon, the period of the bit phenomenon, I can say that the module of that quantity is equal to the module of that quantity for tau equal to 0. Okay? So what all of that becomes? Well, I find that gamma 1, 2 as a function of tau is equal to the module of gamma 1, 2 for tau equals 0 multiplied by this quantity, so exponentiation of I multiplied by beta 1, 2, but then plus 2 pi nu times tau. And this is the very important result that I wanted to establish with you. So it's plus or minus, well, it doesn't matter, because later on, we'll take the real part. So, well, it's of no significance, the difference in sign. It depends. You see, here I took the star on A2 instead of taking it on A1, but in fact, yeah, gamma 1, 2 is equal to that, or it's also equal to that. It's the same, no difference. Yeah, okay? So there's more difference of sign, yeah, between what I have established on the blackboard and what is on the transparencies, yeah, is of no importance, yeah. Now, well, I come back here, and I would like to simplify this expression still a little bit, and I will do it as follows. If I take the real part of that, yeah, this is a module, yeah, so the real part of that is a cosine, yeah, so it will be 1 plus the module of gamma 1, 2 tau equals 0 multiplied by the cosine of beta 1, 2 plus or minus, yeah, 2 pi nu tau. Yeah, and I will close the bracket here. So this is expression, yeah? So don't mind about the difference in sign here, yeah? It's of no importance. It means that on my screen, distant screen, yeah? What I shall see, yeah? Let's assume that the module of gamma 1, 2, yeah, is equal to, well, I cannot tell you to what it would be equal because I have jumped one step. So let's define now the visibility. Well, this will give rise to fringes, of course, yeah, in the observer screen. But now I would like to define what is the contrast, the visibility of the fringes. Yeah. So the visibility, yeah, I remind you, is equal to the maximum intensity minus the minimum intensity divided by the summation of the two, I max plus I min. Okay? So, can someone tell me what is the maximum value of this expression when tau vary? Tau vary means that I'm moving, yeah, in the observer plane. So you agree cosine can go from -1 to +1, yeah? So maximum will happen when cosine is equal to 1. So I max will be equal to 2i multiplied by 1 plus the module of gamma 1, 2 for tau equals 0. Okay. Now I also indicate I max below 2i 1 plus module of gamma 1, 2 for tau equals 0, module close. Now here I have minus and here I have plus. I mean, yeah, I mean will happen for cosine equal to -1. So here it will be minus 2i multiplied by 1 minus module of gamma 1, 2 for tau equals 0. And here, same, plus 2i 1 minus module gamma 1, 2 for tau equals 0, like that. Okay. So it means that the visibility will be equal to what? It's easy. 2i and 2i goes away. So it remains 4i times the module of gamma 1, 2 for tau equals 0, divided by what? Well, here, the module of gamma 1, 2 go away, yeah, because here I have a plus and here a minus. So what remains is 4i. And so what I find, yeah, at the end is that the visibility of the fringe is directly equal to the module, yeah, of the complex degree of mutual coherence, yeah. So it's equal to the module of the complex degree of mutual coherence. Very simple, yeah. Now, yesterday we've seen that the visibility, yeah, can either be 1 maximum when the source is not resolved, or 0 when it is resolved, yeah. So I know now, oh, okay, this is really a correlation coefficient, yeah, which may vary between 0, no no correlation, and 1. Yeah. So now, you see, what I obtain, well, is this a very nice expression that in the screen of Young, if I assume that the source is being resolved, yeah, the source is being resolved. We've seen yesterday visibility equals 0. So it means gamma 1, 2 is equals to 0. So what is the visibility of the fringe? No visibility. So it means the screen is uniformly bright. Yeah, I don't see any interference feature. Now, if you look at a star, point-like star, you don't resolve it. Yeah, the visibility is equal to 1. It means that the complex degree of mutual coherence is equal to 1. And what I see in that case, well, nice fringes with a minimum equal to 0 and a maximum which depends on the brightness of the star. Yeah. And now I have all the intermediate cases, yeah, between 0 and 1. And what we will see next, yeah, so this is the next section, yeah, is that the complex degree of mutual coherence is directly related to the structure of the source, yeah, which is not a big surprise, yeah. But this is the next section, yeah. So what I suggest, because next section, yeah, okay, so we will see in the next section that the module of gamma 1, 2 is directly related to the structure of the source that we are observing, yeah. And before going to that, yeah, I propose to you, well, 2 questions. Let's assume that we are making the Young's holes experiment with 2 point-like holes for the case of monochromatic waves, so not even quasi-monochromatic, and, well, an infinitely small point-like source, yeah? What is the value of module of gamma 1, 2? How much? 0, 0.5, or 1? 1. It's 1. Yeah. It's what we saw yesterday. Yeah, we were looking at the point-like source with the Young's holes experiment, and we were seeing fringes, nice fringes, with I max and I min equal to 0. So it means the visibility equal to 1, complex degree of mutual coherence equal to 1. And now, and what can we say about the source when gamma 1, 2 equal to 0? What can you say? Is that what? Yeah, visibility is equal to 0. It means that we are resolving the source. We are resolving, yeah. Okay. So let's now evaluate, the value of the complex degree of mutual coherence, for the case that we are interested in, namely an extended source, emitting quasi-monochromatic light. And this leads us directly to study the notion of the spatial coherence of light, And so you see, from the Young's experiment, we have relaxed one hypothesis assumption. Light is not monochromatic, it's quasi-monochromatic, Now, what we are relaxing now is the fact that the source is not point-like, it will be extended, And next, and this will be next week, we will assume finite dimension for the apertures in the Young's holes experiment,